Welcome to The Explainer. I am absolutely thrilled you're joining us today, because honestly, we're looking at something that feels totally like science fiction, but it's actually happening right under our feet. Literally. Okay, let's just dive right into this. We are exploring the fascinating concept of harvesting electricity from everyday movement. Think about it, all the walking, the running, the driving that happens across the globe every single minute. What happens to all that kinetic energy? Well, mostly it's just lost. But today, we're going to see exactly how engineers are capturing that movement and turning it into usable power.
Notice these brightly illuminated green tiles scattered across the floor here? Now, this isn't just some fancy lighting design for a busy station. These tiles are actively reacting under the feet of commuters. The people walking by with their luggage, stepping on these exact squares, are actually powering the lights themselves. It's a real game changer.
So it forces us to ask this incredibly provocative question. What if every step you took generated electricity? Imagine the sheer volume of foot traffic in an airport or a subway station or a busy city intersection. If we can harness even a fraction of that mechanical energy, man, we are looking at an entirely new paradigm for urban power generation. Let's start our reverse engineering journey and figure out exactly how these floors are pulling this off.
Section 1. How piezoelectric crystals work, the magic in the materials.
Right, so to understand the glow, we really have to look at the mechanics making these floors possible. We're shifting gears to look under the hood at the underlying science, and it all comes down to a very specific type of material. Here is the formal definition straight from the engineering literature. Piezoelectricity relies on materials that have a specific crystalline structure and ability to convert mechanical energy, stress and strain, into electrical energy. I want you to focus on those two words, stress and strain. When you step on these materials, you're physically deforming them. That mechanical pressure is the literal driver of this power. You aren't just pushing a button, you are physically squeezing electricity right out of a crystal.
Notice how perfectly this visualizes that definition. Over in the bottom left corner, you see those blue arrows pointing down and up, pressing on that gray cylinder? That represents the exact stress and strain we just talked about. And notice what happens the exact moment that pressure is applied? The needle on that attached voltmeter jumps. Pressure goes in, voltage comes out. It's direct, it's immediate, and it's incredibly efficient.
Section 2. Soft versus hard covers, designing the floor. Of course, it's one thing to squish a single crystal in a lab, and entirely another to capture the footsteps of thousands of Russian commuters. Engineers have to make crucial choices about how to best capture that stress and strain across a wide floor area. Let's look at two distinct floor setups here. On the left, you see a setup with a soft, transparent blue cover placed over a grid of yellow piezoelectric crystals. Then, on the right, we have a very different approach. Someone's shoe is stepping onto a hard, solid gray floor plate. Notice the pink arrows showing how the energy travels downward in each scenario.
So the crucial point here is understanding the trade-off between these two designs. With the soft cover, energy generation is highly localized. Basically, only the specific devices directly stepped on generate electricity. If you miss the crystal by an inch, you get absolutely nothing. But with the hardcover, the force of the footstep hits a vibrating plate. That hardcover distributes the vibration across a much wider area, transmitting the energy down to multiple crystals at once. It's a brilliant way to maximize the harvest from a single footstep.
Section 3. The engineering prototype. Inside the mechanism.
So we know the theory, and we know the surface design options. Now we are literally going to lift the floorboards. Let's take a look at an actual real-world mechanical vibration energy harvester prototype built in the lab to test this tech. Looking at the full assembly view up top, you can see the sleek metal floor plate, but more importantly, follow those wires. The unit is plugged directly into an oscilloscope to actively measure the electrical output in real time. This is exactly how engineers know how much voltage is being generated by every single simulated footstep.
Focusing on the main prototype body on the left, let's break down the structural base of this setup. Just guide your eyes to the four corners. You'll see these distinct springs connecting the solid upper plate to the bottom plate. These springs are absolutely vital. They control the compression, ensuring the floor gives just enough to capture the mechanical energy, but then springs back instantly for the very next step.
Now look at the middle of that top plate. Let's zoom in on that mechanism, shown here on the right, rotated 90 degrees. This is the actuating bar array. When the upper plate compresses, this rigid structure acts as a crucial mechanical bridge inside the unit. It takes the broad force applied to the upper plate and focuses it right downward onto the power-generating components below.
And this right here brilliantly illustrates the final piece of the puzzle. Highlighted at the bottom is the stacked piezoelectric beam array. This is the core, guys. This is the engine room. When that actuating bar array pushes down, it bends these specific layered beams. This is where the mechanical vibration we've been tracking is finally actually converted into electricity.
Section 4. Building a smart crosswalk, layer by layer.
We've seen the microscopic crystal. We've analyzed the lab prototype. Now let's transition from the lab back out into public infrastructure to see how this technology is applied at scale out in the real world. Here is a cross-section diagram of what we call a smart crosswalk. This takes everything we've learned so far and totally supersizes it. Notice the silhouettes at the top? We aren't just capturing energy from pedestrians walking across the street anymore. No way. This system is designed to capture the immense pressure of rolling cars as well.
To understand how on earth it survives a 2-ton car and still makes electricity, let me walk you sequentially through the exact journey of a downward force traveling through these 3 engineered layers. It starts at the surface with step 1, moves to a protective step 2, and finishes at the generating step 3.
Let's look at the specifics. Layer 1 is the surface, GE Blue Romark Reflective Road Marking Tape. It has to look and act like a normal crosswalk, so pedestrians and drivers actually know where to go. But underneath that is the secret weapon, Layer 2. This is a hard rubber layer sandwiched between the tape and the power panels. Remember our discussion on hard versus soft covers? This hard rubber is absolutely critical for transmitting that heavy physical force evenly down into Layer 3, which houses the heavy-duty piezoelectric panels. That's where the movements and vibrations finally become power.
Section 5. The future of kinetic infrastructure, looking ahead.
We have journeyed all the way from the microscopic crystalline level, defining stress and strain, right up to smart city grid applications like high-traffic crosswalks. It really changes how you look at the sidewalk, doesn't it? To validate just how important this is, I want to read this direct quote from the source research we've been unpacking today. The power-generating floors can be a major application if we use piezoelectric crystals as an energy-converting material. This isn't just a fun science fair trick. The engineers behind these documents see massive, untapped potential for this to become a standard in how we build our cities.
And that brings us to the end of our explainer today. I want to leave you with a thought to chew on as you go about your day. Look at your environment differently. Think about the places you go, the stairs you climb, the roads you drive. Where else in your daily commute could we harness the hidden power of movement? The energy is already there, literally waiting beneath our feet. Thank you so much for joining me on this deep dive, and I will see you on the next explainer.